Welcome to the first video of our notes for our momentum unit. Here we have impulse momentum notes. In this video, we're just going to be defining a few things, looking at some equations, and talking about a few examples. So when we're talking about momentum, I'm going to skip down to defining momentum before we talk about impulse. And momentum, if you did the reading, is described as a mass that is moving. Now, almost everything we encounter has mass, every object. And we write momentum, we use P, the letter P for momentum, and we write this as a mass, so M, that is moving. And something that is moving has a velocity. So to write this in words, we can say that momentum of an object is equal to its mass times its velocity. All right. And when we're talking about equations, there's three things we want to do. We want to write it using our variables like so. And then we also want to talk about units. So our units for momentum are going to be kilograms times meters per second. And how did we get here? So our equation is momentum equals its mass times velocity. Mass has units of kilograms and velocity has units of meters per second. So we multiply those two together. You can see our units are kilograms meters per second, which can also just be written as this, our kgm over s. All right, and we might revisit this this unit in a second, but the third thing that we want to talk about is our relationships between our variables. So because we have P equals mv, if we want to increase our momentum, if we want to increase P, we can increase M or V. So we can make M larger or V larger, and that's going to make P larger, or we're going to have more momentum. Or vice versa, right? If we wanted to make P smaller, we could decrease our mass, or really. We could do both or just one, or velocity, right? So that's momentum. Now, it says we're going back to Newton's second law, right? So Newton's second law we know as our net force is equal to our mass times our acceleration of our object. And we can rewrite this in a little bit of a different way. So we know that acceleration can also be written as our change in velocity over change in time. So let's bring that down. And we have our net force is equal to our mass times a change in velocity over our change in time. And I can also write this, I can just drop the triangles or the deltas. And our numerator up here looks very similar to something we just talked about, which is momentum. Right, so we can actually write Newton's second law in terms of momentum. And I'm just going to drop the net on this. But we're going to have F equals P over T, or delta P over delta T. And I'm just going to multiply over my delta T. So our delta T's cancel, and we're left with our force times our change in time is equal to our change in momentum. All right. So this is Newton's second law restated. See, we can get back to our original equation up here by just manipulating what we have down here. Now we have this new word that you probably are not familiar with, which is called impulse. Or if you've heard it before, it might not have been used in the same way as we're going to use it. But impulse is just going to be this guy right here. All right, we call impulse, we use the letter I. Impulse starts with an I. We're going to use I. And yeah, this is what impulse is. I equals our force times our change in time, which is also equal to our change in momentum, as we found. So this is our first, remember, we have three things that we want to talk about. One of them is just our symbolic equation. Our second is our units. So the units on impulse is going to be the units of force, which is newtons, or N, times our units of time, which we know is seconds. So this is going to be Newton seconds. These are units of impulse, which actually is the same as kilograms meters per second, because we know that newtons are actually kilograms, which is a mass, times an acceleration, which is meters per second squared. Now we're multiplying by a time, so our s's will cancel, or our seconds will cancel. One of them will, and we're left with kilograms meters per second. So these two match, which is good for us, right? Our units make sense. I think most often we'll deal with kilograms meters per second instead of Newton seconds, but it's good to understand that relationship. And our third aspect of defining something is talking about the relationships of our variables. So I think one way to do this is graphically. So if I have two axes here, one of them is going to be force and the other is going to be time. Now let's just say that I'm using a constant force of like 10 newtons, let's say. All right, and I'm going to move this down a little bit. Lost a bit. All right. And I'm going to apply this for any amount of time. Let's just call it 5 seconds. Okay. Now, my impulse equation, we said, was our force times our change in time. So if my initial time is here at 0 and my delta t, my final time is 5, delta t is going to be 5, and my impulse is, and my force is 10 newtons, so we have 10 newtons times 5 seconds, and it's just going to be this area here underneath my force curve, but right now it's just constant force. So we can see that if we wanted to increase our impulse, or I, there's two ways that I could do this. I could increase my force, which would be raising this guy up to a higher force value. So now we have all of this extra area. Now our impulse is clearly larger than before. Or I could increase the time that I'm applying the force. So if I come out here to, let's just say like 10 seconds, now I have, again, increased my area or increased my impulse. All right, so that's our two ways of increasing impulse. We can increase our force applied or the time that force is being applied over. And again, vice versa, just for completeness. All right, if we want to decrease our impulse, we will decrease F, bring this down, or decrease the time that our force is applied, right? Cut that in half, maybe less impulse. So if you were in class, you would have seen us do this demo with an egg being thrown at a sheet, a hanging sheet, like a bed sheet. And there's the other scenario, which is throwing the egg at the wall, which I don't think we would do in the room. But we have two scenarios, right? So we have the egg at the wall and the egg being thrown at our sheet. And we will be analyzing the momentum changes going on in this demo. We know that the mass of our egg is the same. So hang on, wait, maybe there's a better way to do this. Mass of our egg is equal to our mass in both scenarios. We're going to assume that our initial velocity is equal in both. We're throwing the egg with the same speed, and both eggs are going to end up with the same speed, v final, because they're both going to stop moving. So their final velocity will both be 0. And from this, we can see that if our masses are equal and our velocities are equal, we can say that our momentums are equal. Our initial momentum and our final momentum is equal. Now further, we know that our change in momentum is our final minus initial. And so we know that our changes in momentum are going to be the same. Now, this may strike you as a bit confusing because there's such a different result. In one, the egg splatters all over the place, and the other, the egg should stay, upside down egg, should stay nice and intact. So how do we explain this, right? Our change in momentum, we're going to use an equation from above. We also called our impulse. And the difference in these situations is our impulse for the wall is still equal to our impulse of the sheet, right? Because our changes in momentum are the same. But the difference comes from our variables. So this also equals our force times our change in time, right? Our wall scenario had a higher force, or a bigger force, and a shorter time, whereas the sheet had a smaller force, but a longer time, which came out to be equal. It's like saying that if it's like saying 10, newtons for 1 second is equal to 1 newton for 10 seconds. You're both going to get 10 newton seconds. Only this combination, these two combinations might produce different results. And that's what we saw with the egg. Here's a real life example of our baseball player here. And his coach is telling him to follow through on his swing. And we're going to look at this a little bit closer in terms of momentum. So imagine a baseball player is trying to hit a pitched baseball. Does the hitter want a large change in velocity of the ball or a small change? Remember, velocity has direction. So does momentum, right? The batter wants a big change in velocity. And why is this, right? We're thinking about our direction. The ball, let's say, I'm just going to draw it out. We have our baseball player here, and our baseball coming in at 90. We're in physics class, so we're gonna call it meters per second. So this is our before, and this is going to be a negative 90 meters per second because we just are saying that left is negative. But to be successful and get on base, the ball needs to go in the other direction, right? So when he's done hitting, the ball needs to be going. Just to simplify this, I'm going to draw it horizontally because normally you go, up. But he needs to send it back. Let's just again say with the same velocity, but just in the other direction. And so, I mean, the term big or small is kind of relative, but I would call this a big change. We can see that our change in velocity, which is what we're being asked for. Again, very important to know what we're being asked, is our final minus our initial, which equals 90 meters per second because we're going to the right. Right is positive in this situation, minus our negative 90 meters per second. Subtracting a negative is positive, so our change in velocity is 180 meters per second, which is, if you've ever been to a baseball game, a big change. Now we're talking about momentum, obviously. So does the hitter want a large change in momentum or small? Before I say the answer here, let's look at our equation for momentum, which is, I guess we're talking about changes, so I'm going to include the change version. Change in momentum is equal to our mass, which does not change, times change in velocity. So if we have a large change in our velocity, we're just multiplying our mass and velocity together, so we're going to get a large change over here as well. So this is a large change in momentum. Now, does our hitter want to exert a large impulse or a small impulse? Again, we are going to look at our equations, right? And look at those relationships. So we see that our impulse is equal to our change in momentum. Well, we just said that because we want a large change in velocity, we know that we will get a large change in momentum, which means that we will get a large change in impulse. All right. We're just bringing this relationship down. And we are in physics class. What physics term is the coach telling our hitter to maximize? As he says, follow through. We're going to assume that our hitter is hitting with as much force as he can. So our force is going to remain constant. Our hitter is swinging for the fences. That's going to stay the same. And so the only thing that we can increase is our time. I guess I would say time of contact between the bat and ball. This is what he is telling the hitter to maximize, specifically the time, right? Because again, we can look up and think about if our hitter is hitting with, just to keep it the same, 10 newtons, and he cannot go any higher. This is all out of his reach. The only thing he can do to increase his impulse, if we can't increase our force, is to increase our time, and that's that follow through. So in summary, I'm just going to rewrite some of the equations that we came up with today. So our momentum was our P, which is equal to mass times our velocity of our object. Impulse was equal to our change in momentum, which was also equal to our force times the time. And we also have our change in momentum equation, which is just our normal m times v, but our v is changing. So our change in v. And just to make this super clear, I'm going to organize this. Our impulse here, I'm going to rewrite this guy over here, say I is equal to, and that's that.